Hello, Miss Arsena.
Yeah,
Hello.
hello. Hi. Can you hear me
Yes.
well? Yeah,
Yes.
sorry, I
Yes.
just wanted to make sure that the connection is okay.
Fine. Fine. Yes. Now you
Just
can able to share your screen.
put my screen on.
Yeah.
Um, yeah. And maybe I should share the screen as well.
Yes. 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 Yes.
Um, okay, so let me do this. Yeah. Can you see well? I mean, everything.
Yes.
All
Everything
right.
is coming perfect. Yes. We'll
Oh,
start. We'll start in another 5 to 6 minutes, and
yeah, yeah, sure, sure. I will start at in 5 minutes.
yes.
And but unfortunately, I need to leave 10 minutes earlier, so I
Yes.
will.
No problem. No problem. You can take
Yeah.
it. No problem. Yes.
Okay, great. Yeah,
Yes.
sorry about that. I mean,
No. It's okay. It's okay. It's okay, Arsena. Yeah. Thank you.
so
Yeah.
I think that's okay.
Yeah. Fine. Thank you.
So you're on multiple campuses. Your university is in
Yes.
multiple campuses, right? Right. And there
Yes.
was a national project funding this, or
Like regarding.
it seems to be a very state-of-the-art facilities and everything. So it must be a recent project.
No. Actually, it's not any recent project. Actually,
Okay.
it is from last year. Actually, it's a new university from last year. Before that, we used to have at the different specific, but from 2024, it was a project for with engineering. Actually,
Right.
yeah.
Okay. And do you have many students?
Yeah, right now we are only having around like for last 24-25, we have around 90 students because we only started the first year batch. So
Yeah.
this year we are expecting around another 210. So
Right.
altogether it will be 300 people for this 2 years.
Yeah, of course. Okay. So I wish you all the best.
Yeah,
You're
thank you.
very active, as I can see. In
Yes, yes, yes.
yeah.
And Arsena, maybe I should ask you like maybe in the like if possible we can do some collaboration project also if possible. Maybe I'll drop an email to you.
I'm sorry, I didn't understand the last point.
My point is like we can even plan for having any collaboration project also like within this your university as our university any research project or something about cross domain certification courses or something like that.
Yeah, yeah, of course, we should discuss. I mean, yeah, definitely.
I'll send a separate email to you because you are also the fellow for the institute also. So maybe we can able to plan something. Maybe with your network we can able to build something good for the people of our community also.
Okay. Yeah, yeah. I mean, we should definitely have a discussion about this, and then maybe you can also present um maybe what is the focus of the university, explain a little bit, and yeah.
Yes, definitely. Sure. Thank you.
Yeah, yeah, sure. I think I opened the wrong document. Let me actually, yeah, I will stop sharing and reshare. Sorry.
Yeah, yeah, it's okay.
Yeah, because I have too many presentations. Yes. Okay. A good one. Yes. They should do something about this Zoom because it
Yes,
pop
yes,
up.
yeah, yeah. It's visible now. It's completely fine. Yeah,
Yeah, it's hard to handle sometimes.
yeah. I understand.
So yeah, let me know when we should start, or you want to wait a few more minutes.
Just one more minute, one more minute. We'll start immediately. One more
Okay.
minute. Yeah,
Yeah.
sure. So, hello everyone, welcome to the IEEE Symbiosis Institute of Technology, Hyderabad, and IIC cell of the Symbiosis Institute of Technology, Hyderabad, hosting the SIT Research Talk Series. So, we have been successfully hosting the fourth one today, which is about the on the physical layer security in 6G from theory to practice. So, myself, Sai Prashant, the student affairs of Symbiosis Technology Hyderabad, welcoming all the participants across the world for joining on this good research talk. So let me introduce to you for today's speaker, who is Professor Arsenia Chorti, who is from the Barkhausen Institute University, as well as the IEEE Communication Society Distinguished Lecturer. So without any further delay, I give it to Arsenia to take over. Arsenia, over
Yeah.
to you.
Thank you very much for the invitation and for the chance to speak about physical air security and how hopefully we will see some first um, application, let's say, into 6G for the first time. So the results I will present today were supported by three different projects. So the France 2030, which is a nationwide project for the acceleration of 5G and 6G in France. The Horizon Europe Robust 6G project, it's an SNS JU project, and a CNRS and Singapore collaboration project called EPAL. So just to give the outline of this talk, so I will start with, first of all, the need for new tools in 6G security, and then I will move on to give you a bit of background regarding two of the possible technologies that we can see envision for application in 6G, in more details, physical layer authentication and secret key generation. And I will explain how, in my opinion at least, there is enough ground at this moment for the incorporation of those two techniques in 6G security protocols. And I will finish with a very quick presentation of perspectives and conclusions. So why do we need new tools? I mean, as you all know, security is a rather conservative domain. We don't go and change technologies, let's say, as easily as we do in the radio access network. But with already the introduction of 5G, there were some issues that arose, especially with respect to latency constraints. So, for example, it takes quite a few milliseconds, 20 milliseconds in one study to verify digital signatures, which form a part of a standard authentication protocol, TLS, that was introduced in 5G. A second issue has to do with the scalability. So when we are in a massive low-end IoT regime, the question is, how do we authenticate and distribute secret keys to all of those constrained and very simple devices? And at the same time, we have the let's say, rise of quantum computing. So all of the solutions that we need to propose from now on need to have quantum resistance in terms of possible robustness. And furthermore, if we look a little bit down the road, in 6G, we will incorporate sensing into the standard communication. So we're talking about integrated sensing and communications. And this provides, let's say, a lot of opportunities with respect to reaching context awareness, so physical context in what we are more interested in at the lower layers of the OSI. And this physical awareness, let's put it this way, through the sensing, can actually be a driver for adaptive security, context-aware adaptive security, in which we can incorporate physical air security solutions. So physical air security, most of the time, people think of wiretap coding for the secrecy capacity and so on. But in this talk, I will not focus on these topics. I will actually focus on the potential use of localization as an authentication factor, and furthermore on how we can generate secret keys at two remote nodes by exploiting shared randomness on the wireless medium. So I will start with a few fundamental concepts so that we're all on the same page. So first of all, the localization and the extrapolation of secret keys we can look at them as two operations that are kind of in a balance, in a trade-off. So if we have a high SNR, very good quality link with, we have lots of antennas in our disposal and so on, then of course, and high bandwidth, of course, then of course we can perform high precision localization, which in its turn can be used for trustworthy authentication of static nodes. And when we have mobile nodes, we can think of tracking approaches in addition to that. On the other hand, when we have a high entropy environment, so if there is a lot of, let's say, unpredictability in the environment changes because lots of nodes are mobile and so on. Then in that case, we have the chance, of course, to distill high-rate secret keys, as we will discuss later, and those two operations are in this balance. So one of the two at a given environment, at a given point in time, will be, let's say, better suited for a particular application. Just to give two, I think, figures that will explain these ideas more concretely. For large-scale fading, for example, captured through ray tracers, then we have a snapshot of the environment. This is exactly what we need for location-based authentication. And in that case, the CSI fingerprints or the locations of the nodes on this particular environment are largely predictable. At the same time, for security purposes, they have to be unforgeable, and I will explain what that means in 1 second. And of course, they have to be separable, so when we have different users at different locations, we need to be able to identify them with a fine granularity as much as possible. So on one hand, we have large-scale fading that is useful for authentication, and then on the other hand, we have small-scale fading in the wireless medium. Here we see, for example, the rapid changes in the received signal amplitude, which are reciprocal between two nodes within the covariance time, the coherence time of the channel. So this small-scale fading can actually be a source of entropy to distill secret keys from this shared randomness. And here, unpredictability, from a security point of view, unpredictability is important. And I will also explain what that means and formalize what that means in a second. So when it comes to the requirements for authentication, as they actually formulated in the security community, we need to have existential unforgeability, which basically means that adversaries cannot be verified as legitimate. In our case, when we are looking at location-based authentication, this basically means that a node should not be able to pretend it is in another location by, for example, using precoding and so on. At the same time, the separability means that we should be able to identify, as I said earlier, with fine granularity, two different nodes. With respect to pseudorandomness now, the security community has formulated the requirement for defining a pseudorandom number generator in order to provide semantic security. And to put a very long story in a few words, basically, having seen a large enough output from this number generator, we should not be able to predict not even a single bit from the future outputs. When this is translated to our case, this means that the achievable secret key rate is upper bounded by the mutual information between the two legitimate nodes, A and B, here, which are reciprocal, conditioned on the observation of a potential adversary that can be arbitrarily close to any of those two nodes. And we will see how this translates to a practical example here. So when we look into the secret key generation into a little bit more detail, so the standard protocol involves 3 steps. So we have the excitation of the channel. So here pilots are exchanged. Then we have what we call a reconciliation step, where basically the small differences in what was observed are reconciled. This is achieved with the use of the Slepian-Wolf decoders. And then we have a final step here, the privacy amplification, that is an absolutely necessary step and is actually basically the one guaranteeing this conditioning here in this formulation. So the privacy amplification basically relies on evaluating the conditional mean entropy of what was observed by the user Alice in this particular scenario with respect to what was observed by the eavesdropper, and taking into account side information that was exchanged during the reconciliation process here. And for the estimation of this privacy amplification, there are some available tools online. We have used the FBLOW, which is a machine learning based estimator of the conditional mean entropy. The problem with this estimator is that it takes quite a lot of time. It's a very heavy statistical test, so it can take anything between minutes to hours, and in certain cases, if the environment is low entropy, so it's a static environment, there isn't enough innovation, it can even take days or even more. Okay, so this is the background, and now I want to explain some new, let's say, achievements, some new recent results that allow us to answer some of those questions that were raised. So the first result has to do with robust physical layer authentication from a robust physical layer localization. So here we have a verifier, Bob, who verifies the location of a node Alice by using the angle of arrival as the authentication factor. And then we have an attacker, Eve, which might have an arbitrary number of antennas, even larger than the number of antennas of the verifier. In our system model, Alice has just a single antenna. So the attacker's goal, in order to impersonate the legitimate device, is to minimize as much as possible, to find the optimal precoder, basically, that will allow it to minimize as much as possible the mean square error in the angle of arrival estimation by the verifier. Okay, and here we have provided a full proof. I will not go into the details. You can look them up online. I mean, the gist of it is that this mean square error only achieves a low value that decreases with the SNR, and then, of course, at very high SNR reaches a plateau, only in the case of the impersonator being at exactly the same angle as Alice. So the only case in which we have proven mathematically that the only case in which Eve can pretend to be Alice is if Eve is exactly on the same direction as Alice. And in all other cases, irrespective of the number of antennas of the impersonator, the mean square error reaches a plateau and the attack can be identified. And this is true when we have a digital array MIMO and we can use any of the standard angle of arrival, for example, estimation techniques, such as music or Esprit or any other algorithm. This can be proven analytically. We have verified the analytic solution with using formal verification of the proof. We have validated the solution by simulation, so we're pretty certain this is true. And actually, this is the first ever feature from the realm of physical error authentication that can be proven to be robust to spoofing attacks, to impersonation. So it is unforgeable. A key note here is that this result does not hold if we do not have a digital array MIMO and we change to an analog array MIMO. The intuition here being that in an analog array MIMO, basically, we're dealing with scalars instead of dealing with vectors and matrices, and the localization happens in time through the successive evaluation of the angle from different pilot sequences in time. And this does not provide enough diversity to basically, let's say, lock the actual angle of arrival to the estimation. So to summarize it, if we have a digital array MIMO system, then we can prove that the angle of arrival is a robust feature of authentication. On the other hand, if we have an analog array MIMO system, this is no longer true. And this can actually be used when we discuss trustworthiness more broadly of the sensing, and this can be incorporated into this discussion of trustworthiness. So that was the first part about the unforgeability. Then the second question, the second criterion we put together was that these locations need to be as separable, as identifiable as possible. So here we proposed to deal with this as a classification problem, and furthermore, we propose to deal with this as a hierarchical classification problem, where we imagine that we have a given environment, we observe the CSI data, we then use standard algorithms like music and Esprit to do angle of arrival estimation, and then we have a first stage binary classifier that allows us to understand whether we are in a line of sight or non-line of sight region. And based on the decision here, we go to a line of sight classifier or to a non-line of sight classifier. Why did we make this choice and not have just a single step? Simply because the performance of the angle of arrival estimation algorithms is different if we have a line of sight as opposed to if we don't have a line of sight. So we wanted to separate those two events. And we actually checked this proposed classification approach in a real outdoor environment with a data set that was provided to us by Nokia. So this is the catopsis of the campus of Nokia in Stuttgart in Germany. At this red point here, we have a 64 massive MIMO 50 FDM subcarrier antenna. The user equipment runs can be found along those tracks here, those trajectories that I call tracks in the following. The blue tracks, so this region here are in a line of sight region. The tracks that are denoted with the red color are in a non-line of sight region, and we have run this two-stage classification with those 6 potential classifiers, and we were actually able to obtain a classification accuracy so basically to identify which exact track the user was on, with an accuracy that exceeded 96% in all cases. And with some very recent results that I don't have here, we even reached 99% classification accuracy, in the line of sight even 100%. So basically, we can very, very finely identify the users on those tracks. So the separability is very good. And those tracks, I forgot to mention, those distances here from one track to the next is just 1 meter. So they're very close together. And this is an outdoor environment. And as you can imagine, it's a quite difficult problem to solve. So we have the proof of the unforgeability, of the angle of arrival. We have a demonstration in a real data set that it can work excellently well in separating users, even in outdoor. So then the next question is, why is this competitive, and why shouldn't we not just stick to what we already have in terms of security solutions from cryptography? And the answer is because this is a very lightweight solution. So when we look at, let's say, a standard post-quantum algorithm for signing and verification, which is only a small part of an authentication protocol, if we look at the total number of CPU cycles that are necessary, this is based on IBM's published results, this is much higher than what is required in the case where we perform user authentication using, for example, the angle of arrival. And even in our case, the large chunk of the computational effort goes actually to the angle of arrival estimation. So the classifiers themselves are very, very lightweight, and they can even be further optimized. We didn't put a lot of work into optimizing them. Now, the fact that the angle of arrival is the heavy operation actually is not detrimental, in the sense that to run dilithium and to run any of the security, let's say, cryptographic-based security solutions, there is a silent assumption, and the assumption is that the wireless link has been established. But to establish the wireless link, one approach in order to know where to beam in this massive MIMO environment would require the angle of arrival estimation. So what I'm trying to say here is that we can propose new security protocols where the communication and the security are fused together, and therefore the overall complexity becomes much, much lower, and they are therefore very, very competitive. Because we need to assume that there will be some angle of arrival or some other similar approach that is used when we are setting up the communication link, and this is totally ignored by any cryptographic solution. So I think this is a very strong point for discussion in the future on how physical layer security, and in particular physical layer security authentication, can actually entangle the two operations in one go, and therefore we win a lot. Then we move to the secret key generation, and we discuss how this can be made robust. So in the literature, there have been a lot of attacks. So eavesdropping attacks that I have mentioned before, and how we need to take into consideration the best observation of a potential adversary if spoofing attacks, where we might have an active attacker that can act as a man in the middle and can inject signals to control the secret keys. This is absolutely possible if malware has just one more antenna than the legitimate users. There are denial of service attacks, which in the case of physical area security, they take the form of jamming. And of course, there is all sorts of jamming approaches that can be exploited. Then there is tampering attacks, where basically someone tampers with unauthenticated transmission of site information in order to perform the reconciliation, and so on, so on. So the list goes on and on. But the good news is that for all of those attacks, there are solutions and remedies, and I don't have the time, unfortunately, to go to the details here, but you can have a look at this book chapter if you're interested in more details. There is a lot of published results. So the key message here is that we know how to deal with those attacks. What remained, in my opinion, as an open problem, had to do with the speed, with how quickly we can perform this operation. And as I said, the bottleneck there seemed to be coming from the privacy amplification, because this was a very heavy operation. It relied on some very heavy calculation of the conditional mean entropy. So we decided to basically move towards what we call a context-aware secret key generation. So in a given environment, we assume that we have offline a characterization of the environment, looking at worst-case scenarios, so possibly allow the eavesdropper to be at only a few wavelengths away from the legitimate users. So in our experimental results, we let the eavesdropper be just a single wavelength away from one of the legitimate users, and we call this an on-the-shoulder attack. And so we gathered a lot of observations, and in an offline manner, we evaluated the conditional mean entropy using FBLAU. And then we used those offline estimations to train. In our case, we chose an LSTM network, and can be CNN, or there are other types of networks that can be also useful. So we use supervised learning to train a machine learning unit to basically calculate in real time the necessary hashing rate by a real-time calculation of the conditional mean entropy. And by real time, I mean that on a standard laptop that we ran it was only 0.2 milliseconds. So the latency was very, very late. And we were able to demonstrate all of this in a live demonstrator, where secret key bits were generated on the fly as part of the XX2 and Robust 6G Horizon Europe projects. So everything was incorporated here, and we were able to demonstrate this with in the 6G Summit in Dresden just last May. So where all of this can be useful for? So the first application that comes to mind, and this is something we will be working on in the future, has to do with zero-touch automation, and in particular, one aspect of it, which is the automatic device enrollment. So just to give a bit of background, up to now, when the devices are shipped, so the devices, they are fabricated by different vendors. Okay, it is not possible to at all points have secret keys shared between all the possible different vendors and any, let's say, smart factory in this particular case. So what happens is that when the devices are bought and they arrive at the premises of this smart factory, they have to contact the vendor and they have to set up, let's say, a whole procedure that will allow the devices to accept to connect to the particular network. So it's not at all lightweight to set it up. And then the question becomes, can we actually propose something that might help and move towards a more automated type of solution? So what we thought of is to identify in a given environment authenticated locations. So here, for example, this is denoted by this cross. This is depicted by this cross. And so these locations are authenticated in the sense that we know exactly, for example, based on the previous work, what is the angle of arrival from a specific access point that basically sees this cross here. And the administrator places the device on this authenticated location, and then we can generate a handshake protocol where the location of the device is verified, and after this step we start an exchange of messages to generate secret keys and be able to set up the communication. I think there are a few questions here, so there is some in the chat. So there is a question on how will 6G support the rapidly growing demands for data intensive applications like AR and VR. I suppose this question can be answered in the end. I mean, I actually reached the end of my talk, so maybe, and I suppose it goes much further than just answering security questions. So as just to touch on the question that was placed by the audience, there are new technologies in terms of radio access that have been proposed, including the incorporation of sub-terahertz, the incorporation of reflective intelligent surfaces, and of course, the intensive use of machine learning. So all of this together, I think, can set up the stage for allowing the increase, let's say, of the necessary data rates. That being said, there has been a recent paper. I'm not sure if it was on IEEE Spectrum. I can't really remember which magazine it was, but there was a good case made from a senior engineer in Vodafone that basically 5G, broadly speaking, already covers most of the required data rates for this, even for these very high intensive new, let's say, use cases, including VR and so on. But yeah, of course, there are solutions from the wireless technologies that I mentioned earlier. And in addition to that, and to make a concluding point to my presentation, if we incorporate physical air security, then as I have shown, we can make it really fast. So we can talk about fast authentication using location-based authentication and fast secret key distribution performed pretty much in parallel with channel estimation, okay? And we can look at this fusion of communication and security, which will speed up things a lot. So not only for the data plane acceleration through the new wireless technologies, but also acceleration for the control plane by incorporating, let's say, physical air security. So these are a few relevant publications to my talk. So if anyone is interested, I can share the slides, and I'm very happy to answer any questions. Thank you very much.
Thank you so much, Arsenia. So Dear participants, if you have any questions, please post in the chat window. Any questions?
So let me put the chat here.
Any questions? You can also unmute and you can ask the question. That's all fine. If you have any questions.
Maybe I was too clear.
Yeah, exactly. Any questions more? I think. Yeah, I think that's all. So maybe I think that they are much clear about the topic. Maybe there are no much questions on that. So with this, Arsena, thank you so much for your time. It was a very good talk about specific to the only outcome of the research in your 6D domain. So thank you so much for your time and thank you so much. I understand it's a very hectic schedule for you also, but in that also you agree for your talk. So with this, we would like to end your talk on this point. So kindly accept this token of appreciation from our side, and this will be emailed to you as well. Thank you so much.
I think it's very nice of you. Thank you very much. And thanks for inviting me. And I
Yeah.
will be happy to answer questions even by email if someone.
Yeah, sure. Thank you, Arsena. Thank you so much. Have a great day. So, dear participants, we have posted the feedback link in the chat window. Kindly fulfill the feedback. This is very much important to us. And going forward, day after tomorrow on 13th, we are going to have a talk on the rise of the biometric systems by Dr. Sambit Bakshi, who is the head of the Center for Automation Technology, Department of Computer Science and Engineering at NIT Rourkela, as well as he is the IEEE Distinguished Lecturer from the Biometric Council also. So we would be glad to have you all participants there also. So with this, thank you so much for today and hope to see you all on day after tomorrow. Thank you. Have a great day.
Thank you very much. Bye.
Thank you, Archana. Bye. Thank you.